theory predicts 67. This gap should not exist. Scientists declare a crisis. Our understanding of reality is broken. Two teams, one universe, two different truths. Ancient light says 67. Nearby galaxies say 73. Both numbers are correct. Both describe different cosmic realities. James Webb Telescope confirms the discrepancy is real, like two perfect clocks in the same room, showing different times, both measuring the same flow, yet fundamentally disagreeing. This is not measurement error. This is fundamental physics cracking. Across 7 billion years, the universe's story splits in two. Early cosmos expanded slowly. Modern cosmos rushes faster. Both histories are true, yet they cannot both be true. For 10 years, scientists searched for hidden errors, for flawed assumptions. Every new instrument, every refined technique only deepened the mystery. The universe expands faster than physics allows. Now a radical theory emerges. Dark energy might not exist. We've been chasing a ghost. Professor Wiltshire's timescape model suggests we're seeing an illusion. Gravity warps time itself. Clocks tick slower in galaxy clusters, faster in cosmic voids across billions of years. This creates false acceleration. The universe isn't smooth. It's lumpy like a sponge. Voids expand faster. Clusters expand slower. When we average these rates, we get the wrong answer. We see acceleration where none may exist. This challenges 27 years of consensus, the Nobel Prize-winning discovery of cosmic acceleration. Might be a miscalculation. We invented dark energy to explain what we didn't understand. Einstein was right. Time is relative, but more than we imagined. A clock in a void measures more elapsed time than a clock in a cluster. Both started at the Big Bang. Both tell different cosmic ages. When light travels through this time warp, the stretching we measure isn't necessarily acceleration. It's the result of light moving through regions where time flows at different rates. Think of driving a highway with changing speed limits, 50 miles per hour in some sections, 70 in others. If you only measure average speed, you might think you're accelerating when you're just following different rules. The European Euclid Telescope now tests this theory, mapping the cosmic web in unprecedented detail. NASA's Raman telescope follows in 2027. Within this decade, we'll know the truth. Either dark energy is real, and we must understand its nature, or it's an illusion created by our misunderstanding of time's uneven flow. Both possibilities rewrite cosmology, just in different ways. Meanwhile, new data suggests dark energy itself might be changing, growing weaker over time. The constant force we imagined might be dying. The universe's fate might not be endless expansion, but possible collapse. We stand at the edge of cosmic revolution. Everything we knew about the universe's expansion hangs in the balance. The crisis is genuine. The mystery deepens. Physics itself is being rewritten. If you're ready to question everything you thought you knew about the cosmos, join this journey. The greatest puzzle in modern science is unraveling now, and we're here to witness it. The evolving universe, new insights into dark energy and cosmic destiny. Introduction. The study of cosmic evolution has entered an extraordinary era of discovery. For decades, astronomers have meticulously gathered evidence about the universe's expansion, building what appeared to be a consistent narrative of cosmic history. However, recent observations have begun to challenge our fundamental understanding of dark energy and the ultimate fate of the cosmos. This comprehensive analysis examines the emerging evidence that suggests our universe may be far more dynamic and complex than previously imagined, with profound implications for physics and cosmology. Section 1. The Dark Energy Enigma. 1.1. The Established Paradigm. Satellite missions have provided overwhelming evidence supporting the concept of constant dark energy. Observations from Planck, WMAP, and other space-based observatories have consistently measured cosmic microwave background radiation that aligns perfectly with the lambda CDM model, which posits a cosmological constant as the driving force behind cosmic acceleration. These measurements, combined with large-scale structure surveys, have created a coherent picture of a universe dominated by dark energy with constant density. The constancy of dark energy finds further support in Type Ia supernova observations. These standard candles of cosmology have been meticulously studied across vast cosmic distances, with their apparent brightness providing crucial information about the expansion history of the universe. The consistent dimming patterns observed in distant supernova strongly suggest that cosmic acceleration has remained remarkably stable over billions of years. This stability forms the bedrock of modern cosmological models and has guided theoretical physics for nearly a quarter century. 1.2. The DZ Anomaly. The Dark Energy Spectroscopic Instrument, DESI, representing the next generation of cosmological surveys, has begun to challenge this established view. Located at the Kitt Peak National Observatory, DZ has mapped millions of galaxies and quasars with unprecedented precision, measuring baryon acoustic oscillations across cosmic time. The initial results, while not yet conclusive, hint at potential variations in dark energy density that cannot be easily explained by the standard cosmological constant. The statistical significance of these findings sits in a challenging intermediate range strong enough to demand serious consideration but insufficient to claim definitive discovery. The collaboration has been careful to emphasize the preliminary nature of these results while acknowledging their potential importance. The measurements suggest that dark energy might not be perfectly constant, but could exhibit subtle evolution across cosmic epochs. This possibility, if confirmed, would represent a paradigm shift in our understanding of fundamental physics. 1.3. The Path to Resolution. The DZ collaboration has implemented a comprehensive plan to resolve this uncertainty through continued observations. By 2027, the instrument will have collected sufficient data to either confirm the evolving nature of dark energy or rule it out with high statistical confidence. The expanded dataset will cover a wider range of cosmic time and incorporate improved calibration techniques, reducing systematic uncertainties that currently complicate the interpretation. Independent verification will come from complementary missions scheduled to begin operations within the same time frame. The Euclid Space Telescope, launched by the European Space Agency, will map the geometry of the dark universe using weak gravitational lensing and galaxy clustering measurements. Simultaneously, NASA's Nancy Grace Roman Space Telescope will conduct its own high-precision survey of cosmic expansion. Together, these missions will provide multiple independent lines of evidence to either corroborate or refute DES's intriguing findings. Section 2. The Accelerating Universe in Transition. 2.1. Challenging Cosmic Acceleration. A groundbreaking study led by Professor Young-Wook Lee of Yonsei University has introduced an even more radical proposition that the universe's acceleration may already be slowing down. The team analyzed decades of supernova observations using novel statistical methods and fresh approaches to data reduction and systematic error correction. Their results, published in a series of recent papers, suggest we may have passed the peak acceleration epoch and entered a phase of deceleration. This claim, if validated, would represent one of the most significant discoveries in cosmology since the initial detection of cosmic acceleration in 1998. It challenges the core narrative that dark energy began dominating cosmic expansion approximately 5 billion years ago and will continue driving accelerated expansion indefinitely. The Standard Model predicts two possible futures: either continued acceleration, leading to heat death, or ever-increasing acceleration, culminating in a Big Rip. Lee's analysis suggests a third, previously discounted possibility, that acceleration might be transient. 2.2. The Physics of Changing Acceleration. The cosmological implications of changing acceleration are profound. In the standard framework, gravity acts to slow cosmic expansion, while dark energy works to accelerate it. For most of cosmic history, gravity dominated, causing the expansion to gradually decelerate following the Big Bang. Then, as the universe grew less dense, dark energy became dominant and initiated the current epoch of acceleration. Lee's research suggests we may now be witnessing another transition, with dark energy weakening relative to gravity. This could occur if dark energy density decreases over time, or if gravity somehow becomes more effective at large scales. The analogy of a ball thrown upward illustrates this concept beautifully. Initially, the ball slows due to gravity's pull, reaches a maximum height where its upward motion ceases momentarily, then begins descending as gravity takes complete control. Similarly, cosmic expansion may be approaching its own turning point after billions of years of acceleration. 2.3. Competing Interpretations. The scientific community has responded to these claims with cautious skepticism. While acknowledging the technical sophistication of the analysis, many experts point to alternative explanations for the observed effects: systematic errors in supernova measurements, unaccounted for evolutionary effects in supernova populations, or subtle biases in data reduction pipelines could potentially produce similar signatures without requiring new physics. Different research groups applying varied analytical methods have obtained conflicting results. Some analyses of the same underlying data show continued acceleration, while others support the deceleration scenario. The statistical uncertainties remain substantial enough that neither position can claim definitive victory. This healthy scientific debate drives improved measurements and more sophisticated analyses, pushing the entire field toward greater precision and reliability. Section 3. Cosmic Destiny and the Big Crunch. 3.1. Two Fundamental Futures. The current cosmological debate transcends academic curiosity. It concerns the ultimate fate of everything that exists. One path leads to eternal expansion, where galaxies continue receding from one another until star formation ceases, black holes evaporate, and the universe approaches absolute zero in a state of heat death. The other possibility involves deceleration followed by contraction, culminating in a big crunch, where all matter and energy converge back into a singularity. These scenarios are not abstract philosophical concepts, but represent genuinely different physical futures dictated by the fundamental properties of dark energy and the curvature of space-time. The distinction between them depends critically on whether dark energy remains constant, weakens over time, or possibly strengthens. Current observations cannot yet definitively determine which path our universe will follow, but the answer has profound implications for the very nature of reality. 3.2. The Big Crunch Scenario. If cosmic deceleration continues and eventually reverses the expansion, the universe would undergo a dramatic transformation over hundreds of billions of years. The first signs would appear in the light from distant galaxies. The cosmological redshift we currently observe would gradually decrease, eventually shifting to blue shift as galaxies begin moving toward us. The cosmic microwave background radiation, now cool to 2.7 Kelvin, would slowly warm as photons gain energy from the contracting spacetime. As contraction accelerates, the large-scale structure of the universe would begin to unravel. Galaxy clusters that currently move apart would slow their recession, stop, and then approach one another with increasing velocity. Individual galaxies would eventually merge, disrupting stellar orbits and triggering intense periods of star formation, followed by equally intense quenching as gas supplies are rapidly depleted. The night sky, rather than growing darker with time, would actually brighten as galaxies crowd together. In the final stages of collapse, the universe would heat dramatically. Background radiation would shift through infrared to visible light, then to ultraviolet and X-rays. Planetary atmospheres would boil away, followed by the vaporization of the planets themselves. Stars would be torn apart by tidal forces or consumed by growing black holes. Eventually, even atomic nuclei would disintegrate into their constituent quarks and gluons, recreating the conditions that existed mere instants after the Big Bang. 3.3 Scientific Reception and Theoretical Implications. The physics community remains divided about the likelihood of a Big Crunch scenario. Proponents point to its aesthetic appeal and mathematical elegance, particularly how it enables the possibility of a cyclic universe where each collapse triggers a new Big Bang. This concept resonates with certain string theory and quantum gravity models that naturally incorporate cosmic cycles. Skeptics note that most precise measurements to date still favor continued expansion, albeit at a potentially slowing rate. They argue that the evidence for deceleration remains preliminary and could disappear with better data or improved understanding of systematic effects. The majority position maintains that while dark energy might evolve somewhat, it probably won't disappear entirely or become negative, which would be necessary for a big crunch to occur. Section 4. Early Dark Energy and Primordial Physics. 4.1. Solving Cosmological Tensions. The concept of early dark energy has emerged as a potential solution to several persistent problems in cosmology. Proposed initially to resolve tensions and measurements of the Hubble constant, the theory suggests that a form of dark energy briefly dominated the universe's expansion during its first 100,000 years. This temporary acceleration would have modified the sound horizon scale, potentially reconciling the discrepant values obtained from early universe and late universe measurement techniques. The Hubble tension, the statistically significant difference between expansion rates measured from the cosmic microwave background and those obtained from supernova and other local indicators, has stubbornly resisted resolution through conventional means. Early dark energy offers an elegant solution by modifying the expansion history just before recombination, changing the relationship between observable features in the CMB and the present expansion rate. 4.2. Explaining JWST's unexpected findings. The James Webb Space Telescope has compounded cosmological puzzles by discovering an unexpected abundance of bright, massive galaxies in the very early universe. Standard cosmological models struggle to explain how such large structures formed so quickly after the Big Bang. Early dark energy naturally addresses this problem by enhancing the growth of density fluctuations during a critical period of cosmic evolution. The mechanism works through modified expansion dynamics. By briefly accelerating expansion during the radiation-dominated era, early dark energy would allow density perturbations to begin growing earlier than in standard. When the early dark energy subsequently decayed away, these enhanced fluctuations would rapidly develop into the mature galaxies observed by JWST at redshifts previously thought impossible for such advanced systems. 4.3. Theoretical foundations and predictions. The physical origin of early dark energy remains speculative, with several candidate theories currently under investigation. Most models propose a scalar field that temporarily dominates the universe's energy density before decaying into standard model particles or otherwise becoming negligible. These fields often appear naturally in extensions to the standard model, particularly in theories involving extra dimensions or string-inspired phenomenology. These models make testable predictions that upcoming observations can potentially verify or falsify. Precise measurements of the cosmic microwave background polarization, particularly by the Simons Observatory and CMBS-4 project, could detect the subtle imprints left by early dark energy. Similarly, JWST's continued census of early galaxies will provide stronger constraints on structure formation at high redshifts, either supporting or challenging the early dark energy hypothesis. Section 5. Fundamental Puzzles and Inflationary Solutions. 5.1. The Horizon Problem. The remarkable uniformity of the cosmic microwave background presents one of cosmology's most enduring puzzles, the horizon problem. Measurements show that the CMB temperature is identical across the entire sky to within 1 part in 100,000, despite regions on opposite sides of the visible universe having never been in causal contact according to standard Big Bang theory. This uniformity would be natural if these distant regions had somehow communicated in the past, but the finite speed of light and the universe's age make this impossible in conventional cosmology. The problem becomes even more acute when considering the precise alignment of temperature fluctuations which exhibit coherent patterns across scales much larger than the particle horizon at recombination. 5.2 Cosmic inflation as the solution. The theory of cosmic inflation elegantly resolves the horizon problem by postulating a period of exponential expansion in the universe's first moments. During this inflationary epoch, regions that were originally in causal contact expanded to become much larger than our observable universe. The uniformity we observe today simply reflects this primordial causal connection, preserved through the inflationary stretching of spacetime. The inflationary paradigm naturally explains not only the large-scale uniformity, but also the specific statistical properties of the temperature fluctuations. Quantum fluctuations generated during inflation become stretched to cosmic scales, creating the primordial density perturbations that eventually grow into galaxies and galaxy clusters. This mechanism provides a physical origin for structure formation that aligns beautifully with observational data. 5.3 The flatness problem. Another fundamental puzzle solved by inflation is the universe's remarkable spatial flatness. Measurements from multiple experiments consistently show that the universe lacks detectable spatial curvature to extraordinary precision. The density parameter omega differs from unity by less than 0.001. Maintaining this flatness through conventional expansion requires incredible fine-tuning of initial conditions to approximately 1 part in 1062. Inflation naturally drives the universe toward flatness regardless of its initial curvature. The exponential expansion stretches spacetime so dramatically that any pre-existing curvature becomes undetectable, much like how the surface of a balloon appears increasingly flat as it inflates. This elegant mechanism explains the observed flatness without requiring implausibly fine-tuned initial conditions. Section 6. The physics of cosmic inflation. 6.1. The inflattened field. The engine driving cosmic inflation is thought to be a hypothetical scalar field called the inflaton. Unlike familiar matter and radiation, the inflaton field possesses unusual equation of state parameters that generate repulsive gravity. This negative pressure drives exponential expansion, with the universe doubling in size repeatedly during a brief period lasting perhaps 10 to 32 seconds. The inflattened field maintained nearly constant energy density throughout inflation despite the rapid expansion, creating a feedback loop where more expansion generated more inflationary drive. This contrasts sharply with conventional matter and radiation, whose energy densities dilute rapidly during expansion. The peculiar thermodynamics of inflation enabled the universe to grow from subatomic to cosmic scales in an astonishingly brief interval. 6.2 Reheating and the end of inflation. Inflation concluded through a process called reheating, where the inflattened field decayed into the particles that would form the hot, dense plasma of the early universe. As the inflaton oscillated around its potential minimum, it transferred energy to standard model fields through parametric resonance and particle production, effectively reheating the universe to temperatures sufficient for Big Bang nucleosynthesis. This transition from inflationary expansion to conventional radiation-dominated expansion represents one of the least understood aspects of the theory. Detailed mechanisms for efficient energy transfer remain active areas of research, with connections to both particle physics and gravitational waves. The precise nature of reheating determines initial conditions for the hot Big Bang and could leave observable signatures in cosmological data. 6.3 Quantum fluctuations and cosmic structure. One of inflation's most remarkable achievements is explaining the origin of cosmic structure. Quantum fluctuations in the inflated field were stretched to astronomical scales during inflation, creating the primordial density perturbations that seeded all subsequent structure formation. These fluctuations became imprinted in the curvature of space-time, eventually evolving into the complex cosmic web of galaxies, clusters, and voids observed today. The theory makes specific predictions about the statistical properties of these fluctuations. They should be nearly scale invariant, Gaussian distributed, and adiabatic, all of which have been spectacularly confirmed by precision measurements of the cosmic microwave background. This successful connection between microscopic quantum physics and macroscopic cosmic structure represents one of modern cosmology's greatest triumphs. Section 7. The evolution and refinement of inflation. 7.1 Initial challenges. When Alan Guth first proposed cosmic inflation in 1981, he immediately identified a serious problem, the graceful exit problem. His original model, based on false vacuum decay through bubble nucleation, failed to successfully transition from inflationary expansion to the hot Big Bang phase. The bubbles of true vacuum would never percolate efficiently, leaving the universe hopelessly inhomogeneous. This initial setback nearly doomed the theory, but the core idea proved too compelling to abandon. The solution to the graceful exit problem emerged through the development of slow-roll inflation models, where the inflated field evolves gradually rather than tunneling abruptly. This modification allowed for a smooth, homogeneous end to inflation, while preserving all the theory's explanatory successes. 7.2 Modern inflationary models. Contemporary inflation theory encompasses a diverse family of models with different potential energy landscapes and dynamical mechanisms. These include chaotic inflation, natural inflation, hybrid inflation, and many others, each with distinct observational signatures. While all successful variants share the core feature of exponential expansion driven by negative pressure fields, they differ in detailed predictions about the spectrum of primordial fluctuations. The proliferation of inflationary models reflects both the theory's flexibility and the current limitations of observational data. As measurements of the cosmic microwave background and large-scale structure improve, they progressively exclude large swaths of the inflationary model space. Future observations, particularly of primordial gravitational waves and CMB spectral distortions, promise to further narrow the possibilities. 7.3 Inflation and fundamental physics. Inflation provides a crucial bridge between cosmological observations and fundamental physics at energy scales inaccessible to terrestrial experiments. The inflationary energy scale around 1016 GeV probes physics far beyond the reach of the Large Hadron Collider, offering unique insights into grand unified theories, quantum gravity, and possibly string theory. The ongoing dialogue between inflationary cosmology and fundamental theory continues to yield rich insights. Constraints from cosmology inform model building and particle physics, while theoretical developments suggest new observational signatures to search for. This symbiotic relationship ensures that cosmic inflation remains at the forefront of both theoretical and experimental physics. Conclusion: we are living through a remarkable period of cosmological discovery, with multiple lines of evidence suggesting our universe may be more dynamic and complex than previously imagined. The possible evolution of dark energy, the potential slowing of cosmic acceleration, and the lingering puzzles of early universe physics all point toward exciting new physics beyond our current understanding. The coming years will see an unprecedented flow of data from observatories across the electromagnetic spectrum and beyond. The James Webb Space Telescope, Euclid, Roman, DC, and next-generation CMB experiments will provide complementary measurements with extraordinary precision. Together, they will either confirm the emerging hints of new physics or reinforce the standard cosmological model. Regardless of the outcome, we are guaranteed a deeper understanding of cosmic evolution and the fundamental laws that govern our universe. The questions we confront about the nature of dark energy, the validity of inflation, and the ultimate fate of the cosmos represent humanity's continuing quest to comprehend our place in the grand cosmic scheme. As we stand at this threshold of discovery, we can be certain that the universe still holds wonders beyond our current imagination, waiting to be revealed by the relentless advance of scientific inquiry. The cosmic enigma, from dark energy's secrets to the universe's ultimate fate. Satellite data aligns perfectly with models of constant dark energy. Multiple missions have consistently verified this fundamental parameter. Planck's precise measurements of cosmic microwave background radiation, WMAP's detailed mapping of early universe structures, all point toward an unchanging cosmological constant. Supernova observations reinforce this established paradigm. Their consistent dimming patterns across cosmic distances reveal a story of steady cosmic acceleration. These celestial standard candles have illuminated a remarkably stable expansion history spanning billions of years. Yet DAISY detects a different signal, a subtle variation in the cosmic rhythm, statistically significant though not yet conclusive. This anomaly challenges our fundamental understanding. Potential new physics or mere statistical fluctuation. The DZ collaboration continues its meticulous work, mapping millions of galaxies and quasars, tracking baryon acoustic oscillations through cosmic time. By 2027, they'll gather sufficient data to confirm or refute this intriguing possibility. Independent verification awaits from new observatories. Euclid Space Telescope begins its dark universe survey. Nancy Grace Roman prepares for precision measurements. Together they'll provide multiple lines of evidence to resolve the dark energy enigma once and for all. If dark energy proves dynamic, new questions emerge. Why would empty space's energy density vary? What physical process drives this cosmic evolution? Current theoretical frameworks offer no answers. This would demand physics beyond the standard model. Meanwhile, revolutionary research suggests the universe's acceleration may be slowing. Young Wook Lee's team analyzes decades of data. Their novel approach reveals surprising patterns. We may have passed peak acceleration. This challenges cosmology's core narrative. The Standard Model predicts endless acceleration, leading to cosmic heat death or eventual Big Rip. But new findings suggest a different future. Dark energy weakening, gravity regaining dominance. Think of a ball thrown upward against gravity's pull, reaching its apex before beginning descent. Cosmic expansion may follow similar dynamics. Initial rapid expansion gave way to deceleration. Then dark energy drove temporary acceleration. Now we may be entering a new phase. Expansion slowing as dark energy fades. Gravity's relentless pull reasserting control. The cosmic balance shifting once again. After billions of years of evolutionary change, the scientific community remains divided. Evidence for deceleration remains subtle. Different analytical methods yield conflicting results. Some show continued acceleration. Others support the slowing scenario. What makes this debate profoundly important is the ultimate fate of everything that exists. One path leads to eternal cold isolation, the other to fiery cosmic reunion. These represent real physical futures. The James Webb Space Telescope joins this investigation. Euclid and Roman add their capabilities. Together they'll measure expansion history with unprecedented precision and clarity. We may have answers within 5 years. If expansion reverses, everything transforms. Galaxies approach rather than recede. Space itself contracts over eons. The universe heats instead of cools. Atoms dissolve into primordial particles. This big crunch scenario mirrors the Big Bang, a cosmic cycle of expansion and contraction. Some find beauty in this eternal rhythm. Others remain skeptical, trusting continued expansion evidence. Before modern dark energy's dominance, there might have been an earlier presence. Early dark energy could explain cosmic puzzles. The Hubble tension in expansion measurements. JWST's surprisingly mature early galaxies. This temporary force would push space apart during the universe's first 100,000 years, then vanish without trace, leaving only subtle fingerprints. On cosmic microwave background radiation, the theory remains speculative but testable. Future observations will reveal its truth. Early dark energy would add a new chapter to our understanding of cosmic evolution, linking quantum fluctuations to cosmic structure. We face deeper mysteries still. The horizon problem questions cosmic uniformity. How distant regions share identical temperatures, despite never exchanging information. Inflation theory provides an elegant solution. Exponential expansion in the universe's first moments stretched a tiny connected region into the vast cosmos we observe today. Regions that appear causally disconnected share common history from before inflation. The universe's perfect flatness presents another riddle, an impossibly precise balance of cosmic density. Inflation naturally explains this fine-tuning by stretching any initial curvature to undetectable flatness over vast scales. Space expanded from subatomic to cosmic dimensions in less than a trillionth of a second. driven by the inflated field's strange properties, maintaining constant energy density, while pushing space apart exponentially. Quantum fluctuations during this brief era became seeds for all cosmic structure, linking quantum realm to galaxy formation, the very largest structures in existence, originating from smallest quantum jitters. The first inflation models had serious flaws. Alan Guth identified the graceful exit problem. Bubble nucleation failed to reheat the universe properly. But the core idea proved too powerful to abandon. Scientists refined it into working theory. Slow-roll inflation replaced bubble nucleation, the inflated field rolling gently downhill, rather than tunneling through barriers. This allowed smooth transition to hot Big Bang expansion. Today, multiple inflation models compete, each with different predictions, all sharing core concept of exponential expansion. Ongoing observations narrow possibilities, bringing us closer to understanding cosmic origins. This journey of cosmic understanding continues. Each answer reveals new questions. Each measurement brings sharper clarity. We stand at knowledge's threshold, ready to comprehend universe's ultimate nature. New telescopes deliver unprecedented data. Theoretical models grow more sophisticated. We're living through remarkable discovery era, poised to determine cosmic destiny and our place within this grand story. The search for understanding continues as we listen to cosmic whispers, trying to comprehend existence's music and our role in this magnificent symphony. The universe slowly reveals its secrets, but doesn't uniquely identify one mechanism. Future observations might finally pin down exactly how inflation worked. Until then, we know inflation happened, but the details remain mysterious. The seeds of every galaxy in existence began as random. Quantum jitters smaller than an atom. Quantum mechanics tells us that nothing is ever truly still, even in perfect vacuum. Fields fluctuate randomly at microscopic scales. These fluctuations are tiny, lasting for infinitesimally short moments. Before disappearing, they're the universe's way of being uncertain. At the smallest scales, normally these quantum jitters have no lasting effect on anything large. But during inflation, something extraordinary happened. As space expanded exponentially, quantum fluctuations in the inflated field got stretched. A fluctuation that started smaller than a proton grew to the size of a galaxy, then a galaxy cluster, then even larger. The expansion happened so fast that the fluctuations didn't have time to smooth out or disappear. They froze in place, becoming permanent features of the cosmic landscape. Think of it like taking a photograph of ripples on water. The ripples are temporary and would normally fade away, but if you freeze them in a picture, they become permanent. Inflation did something similar to quantum fluctuations, freezing them into the structure of space itself. These frozen fluctuations became density variations. In the early universe, some regions had slightly more energy than average. Others had slightly less. The differences were tiny. about 1 part in 100,000. But they were enough when inflation ended, and matter formed. Gravity amplified these tiny differences. Regions that were slightly denser had stronger gravity, pulling in more matter. Regions that were slightly less dense lost matter to their denser neighbors. Over millions and billions of years, these tiny seeds grew into the cosmic web we observe. Today, every galaxy exists because of a quantum fluctuation. During inflation, every galaxy cluster, every supercluster, every void traces back to random quantum noise, magnified to cosmic proportions. The universe's largest structures have the smallest possible origin. This is confirmed by observations. The cosmic microwave background shows the pattern of hot and cold spots that correspond exactly to these frozen quantum fluctuations. The statistical properties of those spots match what we'd expect from quantum mechanics. The universe's structure follows quantum rules, scaled up to astronomical size. Scientists can even calculate the exact spectrum of fluctuations inflation should produce. The power spectrum, as it's called, describes how much variation exists at different scales. Inflation predicts a nearly scale-invariant spectrum, meaning fluctuations have similar strength, whether they're galaxy-sized or supercluster-sized. Observations confirm this prediction. The connection between quantum mechanics and cosmology is one of the most profound insights. In physics, the smallest and largest scales of nature aren't separate, they're linked through inflation. What happens at subatomic scales determines the structure of the entire observable universe. But this raises deep questions about randomness and determinism if galaxy locations depend on random quantum fluctuations. Then the universe's structure is fundamentally probabilistic. There's no deeper reason why galaxies formed where they did. It's just quantum chance amplified and frozen. Some physicists find this troubling. Others find it beautiful. The universe's grandest structures emerged from pure randomness, given form by the laws of physics, acting over cosmic time. Either way, every star you see exists because of quantum uncertainty. The cosmic microwave background has strange patterns in its temperature that shouldn't be there. When scientists analyze the cosmic microwave background, they break it down into components called multipoles. These describe temperature variations at different angular scales across the sky. Low multipoles represent large-scale patterns. High multipoles represent small-scale patterns. The Standard Model predicts how strong each multipole should be based on inflation and cosmic evolution. Most multipoles match predictions perfectly, but some don't. The quadrupole, which describes the largest scale temperature pattern, is unexpectedly weak. The octupole, the next scale up, shows strange alignment with the ecliptic plane, the flat disk of our solar system. This alignment makes no sense. The cosmic microwave background formed billions of years before our solar system existed. There should be no relationship between them. These are confirmed anomalies, not measurement errors, though their statistical significance remains debated. The quadrupole problem means the universe has less large-scale temperature variation than expected. Think of it like measuring sound waves and finding that the deepest bass notes are quieter than they should be. The physics that generated all the other frequencies should have generated strong bass too, but it didn't. Several explanations have been proposed. Maybe inflation lasted slightly longer than the standard model assumes, erasing some large-scale fluctuations. Maybe the universe has some large-scale structure beyond what we can observe, affecting how we perceive patterns within our observable patch. Maybe there's new physics that suppresses fluctuations. At large scales, the alignment with the ecliptic is even stranger. The octopole and quadrupole both show preferential orientation toward the plane of our solar system. This was first noticed by the Cosmic Background Explorer satellite in the early 90s, then confirmed by subsequent missions. It's been nicknamed the axis of evil because it seems to violate the cosmological principle that the universe should look the same in all directions. Some scientists think this is just statistical fluke. When you analyze complex data, occasionally you find patterns that look meaningful, but are actually random. The human brain is very good at seeing patterns, even in noise. Maybe we're over-interpreting random alignments. Others think it's real evidence for something beyond the standard model. Maybe the universe has some preferred direction. Maybe our observable patch sits inside a larger structure with its own orientation. Maybe the cosmological principle is wrong, and the universe isn't truly isotropic loop. Quantum cosmology offers one explanation. This theory, which applies quantum mechanics to the entire universe, predicts that the universe might have bounced, rather than starting from an absolute singularity. At the Big Bang, the bounce would leave imprints in the large-scale structure, potentially explaining the multipole anomalies. The bounce idea says the universe was contracting before the Big Bang reached a minimum size, then rebounded and started expanding. During the contraction phase, quantum effects became important, preventing the universe from collapsing to zero size. The rebound launched the expansion we observe today. If this happened, the quantum state during the bounce would correlate large-scale modes in ways that standard inflation doesn't predict. The quadrupole suppression and the peculiar alignments could be echoes of the pre-bounce universe. This is speculative, not confirmed, but it shows how anomalies drive new theories. When observations don't match predictions, physicists develop new models that might explain the mismatch. Sometimes the anomalies fade with better data. Sometimes they lead to revolutionary insights. The multipole anomalies remain puzzling. More than 2 decades after their discovery, a fundamental frequency in the universe's temperature is far weaker than physics predicts. Imagine listening to an orchestra where all the instruments play beautifully. except the bass section, which is barely audible. You'd wonder what happened to the bass. Did the instruments break? Is something absorbing those frequencies? The cosmic microwave background faces this exact puzzle. The quadrupole represents temperature variations on the largest angular scales we can measure. It should be strong, because inflation generates fluctuations at all scales. With similar power, the models predict a certain amplitude for the quadrupole based on how smaller scale fluctuations behave. But when we measure it, the quadrupole comes in significantly weaker. This discrepancy has survived decades of scrutiny. Colby found it, WMAP confirmed it. Planck verified it with even better precision. The quadrupole is genuinely weak, about 30% below predictions. Here's why this matters. Beyond just one anomalous measurement, the quadrupole corresponds to the largest observable structures in the universe. If it's weak, that means the universe has less variation on the largest scales than expected. This could be telling us something profound about how inflation ended, or about the geometry of space, beyond what we can observe. One possibility is that inflation didn't last quite long enough to generate strong fluctuations at the very largest scales. If inflation ended just a bit earlier than assumed, the modes that would become the quadrupole might not have fully developed. They'd still exist, but would be suppressed compared to smaller scales. Another possibility involves cosmic topology. What if the universe wraps around on itself, like the surface of a hypersphere? If the universe is finite rather than infinite, then the largest possible fluctuations are limited by the universe's total size. A weak quadrupole could indicate that. We're seeing the edge of possibility, where the universe simply doesn't have room for larger variations. Think of it like waves in a bathtub versus waves in an ocean. The bathtub limits how long the waves can be. The ocean allows much longer wavelengths. If the universe is more like a bathtub than an ocean, the longest wavelength fluctuations would be suppressed. Some researchers have explored whether we're living in a closed universe with a radius only slightly larger than our observable region. This would naturally explain the weak quadrupole, but other observations suggest the universe is flat, not closed, making this explanation problematic. The weak quadrupole might also connect to the Hubble tension and dark energy mysteries. If something unusual happened in cosmic history that affected expansion, it could also affect how large-scale fluctuations evolved. Maybe early dark energy or time variations in the expansion rate left an imprint on the quadrupole. No explanation has gained consensus yet. The weak quadrupole remains one of several small puzzles in the cosmic microwave background that don't quite fit the standard model. Individually, each anomaly could be a fluke. Collectively, they suggest something interesting might be happening that our current theories don't capture. Future observations will either confirm these anomalies as real signals, requiring new physics, or reveal them as statistical noise That fades with more data. For now, the bass section of the cosmic orchestra plays, inexplicably quiet. Empty regions of space exist that are so large, they shouldn't be possible, according to standard cosmology. In 2007, astronomers found something disturbing. A void in space nearly 1 billion light-years across, far larger than any structure the standard model says should exist. By that time in cosmic history, they called it the cold spot supervoid because it corresponds to an unusually cold region in the cosmic microwave background. But here's the issue. Structures take time to form through gravity. After the Big Bang, matter was nearly uniform. Small density variations grew slowly as gravity pulled matter together. By the time the universe was a few billion years old, structures shouldn't have reached such enormous sizes. Yet supervoids exist. Multiple have been found since that first discovery. These aren't just empty regions. They're organized structures where galaxies cluster around the edges, while the interior remains remarkably empty. The formation process requires coordinated gravitational dynamics over vast regions. Think of it like finding a massive canyon on a young planet. Canyons take millions of years to form through erosion. If you find one on a planet only a few thousand years old, something is wrong with your understanding of either the planet's age or how canyons form. Supervoids present the same problem for cosmology. They exist, but standard models struggle to explain how they form so quickly. One proposed explanation involves dark energy. If dark energy strength varied across space, regions with stronger dark energy would expand faster, creating voids. But standard dark energy is supposed to be uniform, the same everywhere. Varying dark energy requires new physics. Another explanation suggests these structures aren't actually as large or problematic as they seem. Maybe our distance measurements are slightly off, making the voids appear bigger than they really are. Or maybe we're just getting unlucky, observing rare statistical outliers that happen to be larger than average. The timescape model, which treats the universe as lumpy rather than smooth, might also explain supervoids naturally. If expansion varies across different regions, with voids expanding faster than average, then supervoids could grow larger than uniform. Expansion allows the structures form through the interplay of varying expansion rates, rather than gravity alone. This connects to the broader question of whether we can treat the universe as smooth on large scales. Standard cosmology assumes yes. The cosmic web is just small-scale structure, sitting atop a smooth background expansion. But if the web itself affects expansion in important ways, then our smooth universe models miss crucial physics. Supervoids might be telling us that lumpiness matters more than we thought. The universe isn't a smooth fluid that happens to have galaxies sprinkled in. It's a genuinely structured cosmos, where the distribution of matter affects how space expands. Future galaxy surveys will map more of the cosmic web, revealing how common supervoids are and how large they can grow. If they're everywhere and consistently larger than models predict, that's strong evidence for new physics. If they turn out to be rare edge cases, the standard model survives. The challenge is understanding what we're seeing. Are supervoids mundane features that just look strange? Or are they signposts, pointing toward deeper truths about dark energy? And cosmic expansion, the answer, affects how we interpret everything else about the universe's structure. The most powerful telescope ever built just made the expansion problem worse, instead of solving it. When James Webb Space Telescope launched in December 2021, many scientists hoped it would resolve the Hubble tension. Webb's unprecedented infrared vision should reveal details about distant galaxies and stars that earlier telescopes missed. If measurement errors caused the tension, Webb would find them. The crisis would fade. That's not what happened. In 2024, Adam Rees and his team published Webb's observations of Cepheid variable stars in distant galaxies. These pulsating stars act as cosmic yardsticks, allowing precise distance measurements. Webb can see them more clearly than Hubble ever could, reducing uncertainties and improving accuracy. Webb's results matched Hubble's almost exactly. The expansion rate came out at 73 kilometers per second per megaparsec, confirming the higher local measurements. The hope that Hubble had subtle, systematic errors died with Webb's confirmation. But Webb did more than confirm Hubble. It extended measurements to more distant galaxies, farther up the cosmic distance ladder. Every new data point agreed with the pattern. Hubble established the universe expands faster locally than predictions from the early universe allow. This is real, not an artifact of measurement problems. Some scientists had speculated that stellar crowding might bias Hubble's measurements. When you look at distant galaxies, individual stars blur together. If brighter stars happen to overlap with Cepheid variables, you might misjudge their true brightness and calculate wrong distances. Webb's sharper vision should reveal this. If it's happening, it's not happening. Webb can resolve individual stars better than Hubble, and the distances don't change. Stellar crowding isn't hiding a systematic error. The measurements really are correct. This pushes the problem from observations to theory. Measurements aren't wrong. The mismatch between early and late universe expansion is genuine. Something about our understanding of cosmic evolution must be incomplete. Rees, who won a Nobel Prize for discovering accelerating expansion in 1998, stated it clearly with measurement errors ruled out. The exciting possibility remains that we've misunderstood the universe. New physics might be necessary. Webb also observed extremely distant galaxies from the universe's first billion years. These observations revealed more bright, massive galaxies than the standard model predicts should exist. So early, the universe seems to have made large structures faster than our theories say is possible. This ties to the early dark energy hypothesis. If a temporary burst of dark energy accelerated the universe briefly during its first 100,000 years, that would allow structures to form faster. It would also affect expansion in ways that resolve the Hubble tension. Both problems might have the same solution. We will continue observing for years, building up enormous data sets that will test these ideas. But the first results already point clearly toward new physics. The Standard Model explains most of cosmic history remarkably well, but it's missing something important about how the universe expanded within a decade web, combined with other next-generation telescopes, should reveal what that missing piece is. For now, the crisis intensifies with every new observation. Empty space has energy, but the amount makes no sense. According to particle physics, dark energy is often described as the energy of empty space itself, a property of vacuum quantum field theory. Our best theory of particle physics predicts that vacuum should indeed have energy. Particles and antiparticles constantly pop in and out of existence in brief quantum fluctuations. These virtual particles contribute energy to the vacuum. Here's the catastrophic problem. When physicists calculate how much energy the vacuum should have based on quantum field theory, they get an absurdly large number. The calculation predicts the vacuum energy should be about 10 to the power of 120 times larger than what we observe. That's not a small error. That's the worst prediction in the history of physics, off by 120 orders of magnitude. Think of it like predicting someone's height will be 1 inch and finding they're actually tall enough to stretch from Earth to the edge of the observable universe and back trillions upon trillions of times. The prediction isn't just wrong, it's catastrophically, unimaginably wrong. If the vacuum energy were as large as quantum field theory predicts, the universe would have blown apart instantly. After the Big Bang, space would expand so violently that atoms couldn't form, no stars, no galaxies, no structure of any kind could exist. Yet here we are in a universe that clearly has much less vacuum energy than theory predicts. Why is the actual value so tiny compared to the prediction? Nobody knows. This is called the cosmological constant problem, and it's one of the deepest mysteries. In theoretical physics, some physicists think quantum field theory must be wrong. About vacuum energy, maybe. The virtual particles don't contribute. The way we calculate, maybe there's a mechanism that cancels out most of the vacuum energy, leaving only the small amount we observe. But nobody has found a convincing mechanism. Others think we're missing something about how quantum mechanics and gravity work together. Our calculations use quantum field theory and flat space, but the universe's space is curved by gravity. Maybe the calculation breaks down when you properly account for gravity, quantum gravity. If we ever figure it out, might solve the problem. Supersymmetry, a theoretical extension of particle physics, was once hoped to solve this. Supersymmetry predicts that every known particle has a heavier partner particle. The contributions from particles and their superpartners should cancel exactly, leaving zero vacuum energy. But experiments at the Large Hadron Collider haven't found any superpartner particles yet, and the theory is looking less promising. Another idea is the anthropic principle. Maybe the vacuum energy takes different values in different regions of a vast multiverse. Most regions have huge vacuum energy and can't support life. We exist in one of the rare regions with tiny vacuum energy, simply because that's the only place where observers like us could evolve. This explains the observation, but doesn't feel satisfying. It replaces a physics explanation. With a selection effect, the problem matters, because dark energy dominates the universe's energy budget. Understanding why it has the value it does would reveal something fundamental about the laws of physics. It might connect quantum mechanics to gravity. It might tell us about physics at the highest energy scales. It might even reveal that our universe is part of a multiverse. For now, the cosmological constant remains one of the biggest unsolved problems in physics. The universe's expansion depends on it, but we have no idea why it exists, or why it has the value it does. What if Einstein's equations work perfectly in our solar system, but break down across cosmic distances? General relativity has passed every test we've thrown at it. It predicts the orbit of Mercury, the bending of starlight around massive objects, gravitational waves from colliding black holes, and the time dilation experienced by GPS satellites within our solar system and around nearby stars. Einstein's theory works flawlessly, but maybe it fails at larger scales. Maybe gravity behaves differently when you reach distances of millions or billions of light years. This isn't as crazy as it sounds. Modified gravity theories propose that Einstein's equations are approximately correct, but need additional terms that only matter at cosmic scales. These extra terms could affect how the universe expands without requiring dark energy. The acceleration we observe might not come from mysterious energy pushing space apart. It might come from gravity itself, behaving differently than Einstein predicted. One approach is called MONT, modified Newtonian dynamics. Though more sophisticated relativistic versions exist, these theories add corrections to gravity that become important when accelerations are extremely tiny, far smaller than anything we experience on Earth, but relevant for the outskirts of galaxies and beyond. The motivation comes from galaxy rotation curves. Galaxies spin faster than they should, based on their visible matter. Standard physics explains this with dark matter, invisible mass that provides extra gravity. But modified gravity explains it by changing the law of gravity. Maybe both dark matter and dark energy are illusions created by our incomplete understanding of how gravity works. The challenge for modified gravity theories is explaining everything that dark matter and dark energy explain. Dark matter fits observations, from galaxy scales to the cosmic microwave background. Dark energy explains not just acceleration, but also precise details of the universe's expansion history. Any alternative theory has to match all those successes. Some modified gravity theories succeed in certain regimes, but fail in others. They might explain galaxy rotation without dark matter, but can't explain gravitational lensing observations. Or they might explain acceleration without dark energy, but predict a cosmic microwave background pattern that doesn't match what we observe. Recent versions of modified gravity are more sophisticated. They incorporate screening mechanisms that make the modifications turn off in dense regions, like our solar system, allowing them to pass local tests while still affecting cosmic expansion. These theories are hard to distinguish from dark energy observationally because they're designed to mimic dark energy's effects. Testing modified gravity requires looking for subtle differences and how structure grows over cosmic time. Dark energy simply pushes space apart. Modified gravity changes how matter clusters under its own gravity. These effects differ slightly, and next-generation surveys should be able to tell them apart. The DESI results, showing possible evolution in dark energy, could also fit some modified gravity models. If gravity's strength changes over cosmic time, that would affect expansion in ways that looked like evolving dark energy. Einstein himself added a cosmological constant to his equations to make the universe static, then called it his greatest blunder when Hubble discovered expansion. Now we know the constant might actually exist as dark energy. But maybe the real lesson is that Einstein's original equations, even with the constant, aren't quite right. At the largest scales, the stakes are enormous. If gravity needs modification, that revolutionizes physics. If gravity is correct and dark energy is real, we need to understand what dark energy is and where it comes from. Either way, something profound is waiting to be discovered. Two types of stars used to measure cosmic distances give conflicting results, deepening the crisis. Cepheid variable stars have been the gold standard for measuring cosmic distances. For over a century, these stars pulse regularly, brightening and dimming, with periods ranging from days to months. The period correlates precisely with the stars' true brightness. Measure the period, calculate the true brightness. Compare it to observed brightness, and you get the distance. Adam Rice's team has used Cepheids extensively, building the cosmic distance ladder. That gives an expansion rate of 73. Their measurements are meticulous, cross-checked and confirmed by Webb Space Telescope. The Cepheid calibration appears solid, but Wendy Friedman's team argues for a different approach. Using red giant stars, these are aging stars that have exhausted hydrogen in their cores and expanded to enormous size. As they evolve, they reach a maximum brightness before transitioning to helium burning. This maximum brightness, called the tip of the red giant branch, is remarkably uniform. Red giants make excellent standard candles. Friedman's team published results in 2024 using red giant measurements from Webb and Hubble. Their expansion rate came out around 70, lower than Ries's 73 but higher than Planck's 67. This splits the difference, suggesting the Hubble tension might not be as severe as Ries claims. This disagreement isn't about competence or carefulness. Both teams are world-class, meticulous about systematics, and transparent about their methods. They're using different stars as calibrators and getting different answers. Someone is right or both are missing something subtle. The controversy centers on which stars make better calibrators. Cephides are brighter, allowing measurements to more distant galaxies. But they're complicated. Young Cephides behave differently from old Cephides. Metallicity affects their brightness. Extinction from dust can bias measurements, if not corrected properly. Red giants are simpler in some ways. The tip of the red giant branch is a clean, physical transition. That happens at a well-defined brightness. But red giants are dimmer than Cephides, limiting measurements to nearby galaxies. And identifying exactly which stars are at the tip requires careful analysis. Ries's team argues that Friedman's sample of Type 1, a supernova used for calibration, is too small, potentially introducing bias. Friedman's team counters that Ries's Cephide calibrations have hidden systematics that haven't been fully accounted for. This disagreement matters because it determines whether the Hubble tension is a crisis requiring new physics or a measurement problem that careful work can resolve. If Cephides give 73, and that's correct, the tension with 67 is enormous. If red giants give 70, and that's correct, the tension shrinks significantly. Some researchers have tried using completely independent calibrators to break the tie. Gravitational lensing, where massive objects magnify background galaxies, provides distance measurements that don't rely on standard candles. These measurements tend to favor higher expansion rates, closer to 73 than 67 other methods. Using mirror variable stars or water mazes in distant galaxies also tend toward higher values. The preponderance of evidence leans toward Ries's higher number, but Friedman's concerns about systematics remain valid. Future observations with Webb will help. The telescope can observe both Cephides and red giants in the same galaxies, allowing direct comparison. If both methods give the same distances, one set of calibrators is being used incorrectly. If they continue to disagree, something deeper might be wrong. With our understanding of stellar evolution, the calibration war continues, with the fate of cosmology hanging on which stars we trust. The exploding stars we use as cosmic measuring sticks might not be as standardizable as we thought. Type 1, a supernova, happen when white dwarf stars accumulate enough mass to trigger runaway nuclear fusion. The explosion destroys the star completely, releasing energy in a remarkably consistent way. This consistency makes them perfect for measuring cosmic distances. Observe a Type 1, a supernova. Measure its brightness and you know how far away it is. These supernova were used to discover accelerating expansion. In 1998, they remain the primary tool for measuring the universe's expansion at moderate distances. The entire cosmic distance ladder depends on them, but recent observations reveal complications. Not all Type 1 supernova are identical. Some are slightly brighter or dimmer than average. Some fade faster or slower. The variations are small, but not negligible. When you're trying to measure expansion to 1% accuracy, astronomers have developed sophisticated techniques to standardize these supernova. They correct for the brightness decay rate correlation. They account for color differences. They calibrate against nearby supernova, whose distances are known from other methods. After corrections, Type 1a supernova become excellent standard candles. But what if the corrections themselves introduce systematic errors? What if the way supernova exploded has changed subtly over cosmic history? Stars in the distant past had different chemical compositions than modern stars. Less heavy elements means different explosion dynamics. These differences could bias distance measurements in ways we don't fully understand. Some researchers worry about dust. Light from supernova travels through interstellar and intergalactic space. Before reaching us, dust can absorb and scatter light, making supernova appear dimmer and therefore farther away. We correct for dust absorption using color measurements, but those corrections rely on assumptions about what kind of dust exists. If distant galaxies have different dust properties than nearby galaxies, our corrections fail. We'd systematically overestimate distances to distant supernova, making the universe appear to be expanding faster than it really is. The acceleration might be partially or entirely an artifact of incorrect dust corrections. Other complications involve the progenitor systems. We're not entirely sure how Type 1a supernova form. The traditional picture involves a white dwarf accreting matter from a companion star until it reaches critical mass. But some supernova might result from two white dwarfs. Merging these different formation channels could produce supernova with slightly different properties. Detailed studies suggest these effects are small, not large enough to explain away the Hubble tension entirely, but they add uncertainty. Every additional source of systematic error makes the measurements less reliable. The good news is that independent methods now confirm the supernova results. Gravitational lensing Cepheid variables and red giant stars all point toward similar expansion rates. If supernova had huge systematic errors, the other methods wouldn't agree. The consistency suggests the supernova measurements are fundamentally sound, but small biases could still exist. Shaving even 0.5% off the measured expansion rate would ease the Hubble tension slightly, confirming that supernova are truly reliable. Requires understanding them better. That means observing more supernova, studying their host galaxies, and modeling the explosion physics in greater detail. Webb Space Telescope is now observing supernova in the early universe, when cosmic conditions were very different from today. These observations will test whether supernova behave consistently across cosmic time. If early supernova look systematically different, we'll need to revise our distance measurements, and maybe our conclusions about dark energy. The rulers we've been using to measure the universe might need recalibration, a new measurement using a nearby galaxy cluster. Just push the expansion rate even higher than before. Dan Skolnick's team published their latest results in January 2025, and the numbers shocked the cosmology community. 76.5 kilometers per second per megaparsec. That's higher than any previous reliable measurement. It's not just confirming the Hubble tension, it's intensifying it. The measurement used the Coma cluster, a large group of galaxies, only 320 million light-years away. This is our cosmic backyard, close enough to measure distances. With exceptional precision, the team observed Type 1, a supernova in galaxies within the cluster, calibrating distances carefully. The Coma cluster has been studied for decades. Its distance was already well constrained by multiple, independent methods. Using it as the first rung of the distance ladder grounds the measurement in solid, nearby observations, rather than relying on long chains of calibrations that accumulate uncertainty. The result is robust. The team checked for every possible systematic error. They varied their analysis methods. They used different supernova samples. The answer kept coming back around 76. This isn't a fluke or a mistake. It's a genuine measurement. What makes this significant is that it's independent of the Cepheid controversy. Friedman and Rees disagree about whether to use Cepheids or red giants for calibration. Skolnick's measurement bypasses that debate entirely by starting with a nearby cluster whose distance we know from multiple methods. The higher expansion rate emerges, regardless of stellar calibration issues. This eliminates one possible escape hatch from the Hubble tension. If the tension came from problems with Cepheid calibration, then measurements not using Cepheids should give different results. They don't. The high expansion rate appears real. 76.5 compared to 67 is a 13% discrepancy. That's enormous in cosmology. I imagine two teams measuring the age of Earth, and one getting 4.5 billion years, while the other gets 3.9 billion. Both can't be right. Something fundamental is wrong. The tension now qualifies as a crisis. By any reasonable standard, it's not going away with better measurements. It's getting worse. Every new, more precise observation makes the discrepancy larger and harder to dismiss. This forces a reckoning. Either measurements from the early universe are wrong, or measurements from the nearby universe are wrong, or our theory connecting the two is wrong. Measurements appear sound. The instruments work, the methods are validated. So the theory must be incomplete. The standard model of cosmology assumes dark energy is constant, and space expands uniformly, according to Einstein's equations. Maybe dark energy isn't constant. Maybe it evolved over time or varies across space. Maybe Einstein's equations need corrections. At cosmic scales, maybe. The universe's lumpiness affects expansion more than we account for. All these possibilities are now on the table, taken seriously by researchers trying to resolve the crisis. Within a few years, data from Euclid, Raman, and continued observations from Webb should narrow the options. We'll either find new physics that explains the tension, or discover a subtle systematic error everyone missed. But right now, with the data we have, the universe expands faster than our best theories predict. It should, and nobody knows why. The answers could rewrite everything we understand about reality. This isn't hyperbole. The expansion rate of the universe determines its age, its fate, and the validity of fundamental physics theories. If we're wrong about expansion, we might be wrong about dark energy, dark matter inflation, or even general relativity itself. The implications spread through all of cosmology and into particle physics. Here's what the next decade will bring. The Euclid satellite is already mapping the cosmic web with unprecedented detail. It will measure how galaxies cluster and how that clustering has evolved over billions of years. Different expansion histories produce different clustering patterns. Euclid will distinguish between constant dark energy, evolving dark energy, modified gravity, and the timescape model. NASA's Raman Space Telescope launches in 2027. It will observe thousands of supernovae across cosmic history, tracing the expansion rate with precision no previous mission could match. Raman will also study gravitational lensing, providing independent distance measurements that don't rely on supernova or Cepheid's ground-based observatories, like the Vera Rubin Observatory, will survey billions of galaxies, creating three-dimensional maps of cosmic structure. These maps will reveal whether supervoids are common or rare,